Hello, welcome to the next video for electric fields. Today we're going to look at charged particles in electric fields and electron guns. So when we say a charged particle, it could be an electron, a proton, an ion, a molecule that has a charge, anything that carries a positive or negative charge basically, and it will experience a force in an electric field. Now most commonly we're talking about electrons, but we also might talk about ions. And so this is what's basically going to happen. If you have a charge with a mass, or just a mass, under the influence of gravity, it's going to fall like this, and it occurs because the force of gravity is always acting down, and we've done this in projectile motion. Now a charged particle is similar but different. If you have a charged particle, and this is our electric field, so if I put a positive particle just there, it would experience a force, remembering that we defined an electric field as the force that an imaginary positive test point would experience, the direction of the field, and so it would experience a force in that direction. And if I put it over here, it would also experience a force in that direction. If I put a negative, let's make that a little bit bigger, if I put a negative, it would experience a force up like so. That's a bit big, I think. Now if we remove that writing, alright, and we look at this diagram, what we're saying here is a negative charge is experiencing a force in that direction, and it would result in a path that way, and a neutral charge would go straight through the electric field, and a positive charge would experience that sort of motion. Now the force is, for this one, is always down and always has the same magnitude, and this one, for the negative, it's always up. Now try and remember that, because when we do magnetic fields, charged particles in magnetic fields, it is different, and you have to remember the differences between the two. So in this case, this charge, if the plate was down here and this charge was positive, it would eventually hit the plate, because it's always accelerating, because it's experiencing a force, F equals ma, so it's accelerating towards the plate. And the negative charge, now with this electric field, this of course would be our positive plate, it would experience a force and effectively be a parabola, because it's always experiencing a force towards the plate, so it's going to accelerate. Much like in projectile motion, we wouldn't go up, but we accelerate, and so each time it's getting faster and faster towards the surface of the ground. We have to use those sorts of same analysis of motion and equations of motion and F equals ma that we would for an electric field. Bit confusing? Hopefully I haven't confused you too much. Alright, let's look at some of the examples, and we'll do a couple of things to help you understand. Click. Now, there's a couple of Java things that I'll put on the OneNote for you. If I can bring it across, I've got to use my mouse. Here's the first one. This is called charges and fields. And so what you can do here is you can bring across positive and negative charges, and if you show the electric field, that's the way the electric field would go. And we can use this little counter to measure the equipotential between those, and you can change it to nope, don't want to do that. Change it to high res, and there it goes. And if we wanted to throw in another one, okay, we start seeing the variations in the electric field. That's a fairly simple one. Let's get rid of that. Now let's bring the next one across. This one's a little bit different. In this case, you put charges This is called Electric Field of Dreams. You'll find it on the OneNote. We add a charge to it. There's a charge. There's the electric field, because I think this is a positive or negative charge. Let's define this. Where's our properties? Properties, here we go. Somewhere it should say it's a minus charge. There we go. So the electric field moves towards it. So this is a point charge, and we can give it a velocity and it will keep moving. Now if we add another one, now we've got two negative charges. They will interact, and you can see that when they get close to each other they experience a force of repulsion. The electric field is varying, and we can keep adding more, and they'll never get really close to each other, and some will get acceleration because they're experiencing a force, some will get deceleration, and it's the whole interplay of electric fields. And this is sort of what's happening with electrons in metals, and when you have the delocalized electrons, it's happening electrons in orbitals as well. So we can get rid of that one. You can play with that one. Now the one I really wanted to show you was electric field hockey, which is a variation of the others. Here you have a positive charge. Now I've got to try and remember how I did this. That's it. And what you do is you put a positive charge there, you get a force line, you see, and that shows you the force it would experience, and you go start, bang, goal. Okay, that's pretty easy. Then you try and do these ones. So here's a barrier. Let's go reset. And so obviously you can't send it there, but you want to have one here, and you go bang, whoop, missed. Alright, so you can vary things, and you work your way through various objects. This is really good to get you to understand how forces and electric fields interact. And then finally this one here. If you can do this one, you're a legend. So I want you to have a go at those, and just remember this, because here I go. This is how I did it. Whoops. Oh, go back. Okay, let's get rid of that. My face is there, and look at this. 176 times it took me to finally get in the goal. It was tricky. Have a go. See if you can better it. Let me know if you do. It will teach you a bit. Now, back to electron guns. So this is a electron gun. It's quite a large one, and they come as a much smaller size than that. This is an experimental one used for various experiments. Let's have a look. What is an electron gun? Well, this is the schematics of the most simple form of electron gun. First of all, you have a filament, and so that's a bit of tungsten wire that has a voltage, a current put through it, much like a filament in a light bulb or a heater. It heats up, and because it gets so hot, it bubbles off electrons. Now normally those electrons just bounce back onto the filament, but in this case what we're going to do is we've got a electric field here. So we've got two plates. This plate is negative, this plate is positive. We've got a high voltage between them, so we've got a strong electric field. So the electrons that bubble off the filament find themselves in an electric field, so they experience a force and they're attracted to the positive plate. There's a hole in the positive plate, so some of the electrons will get flung through the plate, and as soon as they get through the plate they don't experience much of an electric field, so they then move with a constant velocity. That's the electron gun, and that's the basics of it, and people have tweaked it and varied it in various ways, but that's what you need to know. And the physics behind it is basically now we have voltage equals, now this would be the work done. So in this case they say a gain in potential energy, but we're actually talking about a gain in kinetic energy, because I would prefer we just call that work divided by the charge, rearrange that, and because the work done is at kinetic energy is half mv squared, so we can rearrange this one to QV. Capital V is voltage, remember, and then the voltage of the electron gun is the square root of 2 times the charge of the electron times the voltage divided by the mass. Notice that the distance is not necessary because, whoops, let's go back, I'm having a bit of trouble today. It doesn't matter the distance between this plate. It's going to be the same amount of work because you're crossing the same potential difference. And so the plates could be very close together, or they could be a long way away. The same amount of work is going to happen. It just takes longer for the electron to go from plate 1 to plate 2, depending on how far apart they are. Okay, so make sure you understand this diagram and the little bit of formulas there. And let's do an example. Hopefully you can read that. It says, if the accelerating voltage in an electron gun assembly is 350 volts, determine the kinetic energy of the electrons as they leave the gun and the velocity of projection into the evacuated space outside the gun plate. So all this is happening in a vacuum, I forgot to say, because otherwise the electrons would be colliding with things and slowing down. Okay, hopefully my mug shot isn't obscuring too much there. Now how do you do it? Well, work equals the charge times the voltage, W equals QV, put it into the formula, standard units, okay, and we get our answer in joules. And then the exit velocity, we can work it out longhand if you like, or put it straight into the formula, which unfortunately isn't on your information sheet, but recognizing that the gain in energy is as kinetic energy, you can put the numbers because you know the mass of an electron and you get this velocity. So all the electrons exiting the electron gun will be exiting with this velocity as long as they haven't hit anything else, pretty much so. Alright, so you've got a couple of questions to do now. Question 26 on page 464. Have a go at it. It's pretty standard, and any problems yell out in class please. And these are real life guns, much more miniaturized, and this gun actually has 3 beams coming out of it, so effectively it's 3 guns. And these were used in televisions, the old school televisions, the big things we used to call cathode ray tube televisions. And they're also electron guns are used in mass spectrometers. This is an example. You have your sample, which is put into some hot metals, hot elements, tungsten elements, and what that does is it vaporizes your sample, so you end up getting some positive ions. You accelerate it through an electric field, you come out with a beam. Now because the ions might have different masses, they'll get accelerated to different velocities, so slightly different variation on the electron gun. And over here you've got a magnetic field. Now we haven't done magnetic fields, but when we come to do it you'll understand what they're doing here. You could just as equally have electric fields. They cause a force to cause a bend to occur, and then you separate from the most massive ions, take the widest curvature, and the least massive have the greatest curvature. And that's related to circular motion. And that's a mass spectrometer used to sample very small amounts of lots and lots of different things, pretty standard chemical and physics equipment in most good labs nowadays. And this is just another example. There's the sample being ionized, bang bang bang, and you're separating the isotopes of magnesium. And it's also, I forgot to mention, it's also a way of separating isotopes, much more efficient than a chemical technique, which is relying on the very subtle differences between isotopes, whereas this is relying solely on the variation in mass. So the physicists know how to work it out. Now a cathode ray tube is what we used to have in our old televisions. Have I still got one? No. But people still use them, nothing wrong with them. And so you'd have your electron gun, you'd have your plates that deflect the beam. This is the front of the screen, and your electron beam would move up and down and across this plate, depending on how much it's being deflected vertically and horizontally. And on this screen here you'd have phosphors that when struck by the electrons would give you the colours that you see on the TV screen. And this is just a mock-up of one. You have your 3 guns producing the beams of electrons. They're coloured here, but they're not. They're just beams of electrons. And then they go and the beams, the red or the green beam hits the green dots, and the red ones hits red and blue, so on. And this moves across the screen and up and down very quickly, faster than the human eye can see, and that's how your picture is built up. And this is just another example of the electron gun. Now all this technology is being phased out. It's being replaced by flat screen TVs that use LEDs and LCDs and all sorts of things. And we'll actually talk about whether or not these things are dead in terms of technology. They're not. They're still going to be used. To get your colour screen, you have a mask, and the beams have to fire through that mask so they hit exactly the right dots. And if you hold up a magnet to an old TV, you can move this mask, and therefore the beams hit the wrong colour dots and you can see some colours. I think I might put a video on the OneNote that shows some people mucking around with a TV, how to wreck a TV basically. Put a magnet on the front of it, and this little animation says it. And all this is happening at thousands of times, so each beam is firing and hitting the corresponding dot because they've got to go through the mask, and then you're building up the colour. And the beam goes across the screen and down and across and down so fast that you don't actually see it happening. So the next video will be some applications of electric fields, and we'll talk a lot more about how we actually use electric fields in today's world. Cheerio!